start with motivating a little bit why ultra-relativistic collisions is an interesting topic to study from at least a theoretical perspective, and perhaps also there might be some observational consequences. As I said before, the broader context of this talk is to explore the dynamical strong field regime of relativity. So I'll spend a few minutes first giving my personal taste of the history of this over the last 100 years, motivating why it's interesting, and then at least claim that as of today, this is a realm of relativity that's completely untested or unconstrained by observational experiment. That's hopefully going to change very soon with various observations coming online. But at the moment, this is a regime which is completely untested. I'll then show a few specific results looking at what happens when two particles, fundamental particles, classical models of particles like black holes or solitons collide when they're traveling at ultra-relativistic velocities. So the total energy of the space-time is dominated by the kinetic energy of these particles. And then we'll conclude with some open questions, and in particular the connections between these finite boost collisions that I'll show you and the infinite plane-fronted gravitational wave collision problem. So here this is my some personal sort of reflections on the history of this part of the field equations. I'm not trying to make it a very exhaustive history, and I'm not trying to give everyone credit that deserves credit here. Again, it's just my sort of organizing my thoughts around this subject. And in a few slides, I'll get a little bit more precise by what I mean by the dynamical strong field. But essentially, so I'm going to break apart the last 100 years to several stages. And first, what I'm calling the discovery of the dynamical strong field occurred essentially the same year with Schwarzschild discovering the first black hole solution in 1915. And within the next few years, the various cosmological solutions, Friedman, Lamarche, Robertson, Walker, de Sitter, etc. So these are examples of solutions in this dynamical strong field. So very soon after Einstein published the field equations, this aspect of general relativity was known explicitly. There were exact solutions that described this. But in subsequent years, perhaps the next 2 or 3 decades, which I'm calling the dark ages here, very little about these solutions were understood or properly interpreted. So, for various reasons. I think one is because if you took at face value what the solutions were saying, particularly black hole solutions, some of the predictions or the consequences are so bizarre. You can imagine what the notion of 20th physics was at the beginning of the 20th century, that people just couldn't accept it. And for other, perhaps more technical reasons, for example, the notion of gauge invariance, coordinate invariance in classical theory, as in general relativity, wasn't very well understood. So there was a lot of misunderstanding of these solutions in the first few years after the discovery of the solution. So around in the 1960s, plus or minus a decade, there was sort of the Renaissance. And it occurred simultaneously on two fronts. One at the theoretical level, where many researchers really started to understand the nature of these solutions that had been discovered so long ago. In some sense, this would have been great if that had been the only thing that had happened. But I think why we are where we are today, why relativity is still at the forefront of researching in physics and astronomy, is not only to then do people start understanding these solutions, but there were astronomical discoveries which implied that these solutions were really relevant to the universe. They weren't just interesting theoretical solutions in some strange regime of a theory. It actually seemed that there were places in the universe that required this dynamical strong field to explain. So quasars, neutron stars, pulsars, the cosmic microwave backgrounds, the universe on large scales. From that time till now, I'm going to call somewhat provocatively the inverse dark ages. And I think that if we think of where we, at least the way that I think about black holes today, in the time since then, there really hasn't been evidence or observations that some of those most extreme predictions of relativity really are correct. But the black holes have become almost a common everyday sort of experience, especially for us physicists and mathematicians and astronomers. We in some sense take them for granted. And so, in the years since then, it's almost like the opposite of dark ages, where they would be misunderstood and dismissed. In some sense, they perhaps understood too well, they take it for granted. And there's sort of a couple of reasons why I think perhaps we shouldn't do that. And one is, again, if you think about what they imply, about the evolution of the universe on large scales and black holes, it's really some astonishing predictions. And the astonishing predictions really demand an astonishing level of evidence before we accept them as, in some sense, a truth, in some sense, a truth about nature. Another reason to perhaps be a bit skeptical about the dynamical strong field is if you think of some of the deepest problems in theoretical physics today, in particular dark energy, and perhaps just loosely just saying quantum gravity, the fact that the Einstein equations, the left-hand side is classical, the right-hand side, when you couple it to matter, all matter is quantum. Just from some sense of philosophical or mathematical sense, those equations, they're nonsensical. So we know that there has to be some superseding theory that makes sense of it. We call it quantum gravity for a better word. And both the puzzles of dark energy and something through Rosetta Stones that have been guiding people for the search of what this quantum gravity theory is, in particular black holes, black hole entropy, all rely on this strong field of law that we haven't got independent confirmation of yet. So before I say a little bit more about that, let me just try to be a little bit more concrete about what I mean by the dynamical strong field regime. So first, it's not easy to characterize. There are a couple of issues. One is there's no intrinsic scale to the field equations, in particular the left-hand side, the vacuum side. And of course, because of the covariance, even sort of very mild solutions, say in Minkowski space, you can write it in coordinates where things look very bizarre and strange. So it's not easy to define. But I'm going to sort of somewhat loosely and a little bit more concretely define it as the regime where the dynamics of space-time, all the kinematics, so the single isotope black hole solutions, exhibit the most sort of extreme nonlinearity that's possible in the field equations, and or the dynamics of what a particular scenario, the radiative degrees of freedom are most strongly excited. So the first aspect we can sort of slightly more quantitative to characterize a strong field regime. Now we have to introduce some length scale and some mass scale. So if you introduce the total amount of matter or energy M and confine it to a region of size R, we expect to approach this nonlinear regime in this ratio, essentially the compaction approaches 1. So essentially, if we can compress things to within a Schwarzschild radius. To look at the dynamical aspects, we can appeal to quadrupole physics, which has been discussed quite a few times in the last couple of days. So this is the quadrupole formula, saying the power in gravitational energy is the third time derivative of the quadrupole moment squared. So order of magnitude, the quadrupole moment is the moment of inertia of the source. If we introduce a time scale t now, this is dimensionally what the third time derivative of the quadrupole moment is. And now to get to this side of the strong field regime, or let's say, how can we maximize the power that's produced by a time-varying quadrupole moment? Well, first let's make this, let's put the mass and the radius in the strong field regime as I defined on the previous page. And also let the source change on the characteristics time, that's the light crossing time of this region. And if you plug those numbers in, you get that the power approaches the Planck luminosity. Well, this is interesting. The Planck luminosity in GR doesn't have an age bar. And the naive thing of the Planck units or where quantum gravity is going to be relevant, but at least what this is telling us, just even in classical GR, that this is a scale where interesting things are going to happen. And the many sort of thought experiments that you can do that, if you try to actually radiate in such a causal fashion, come to a system which radiates energy that's above the Planck scale and form black holes generically, or possibly. Okay, so having sort of defined the strong field as that, isn't relevant to the universe. I think most definitely that's not in question. There are definitely regions in the universe where if GR is right, that strong field comes into play. On the other hand, it's mentioned that in the sense that are any of the observations sort of over-constrained that we can actually test the theory, and at present I'd say not. And if you look at some places,
pulsars, neutron stars, sort of the place where we have measurements of radiation in a minor pulsar, that's emitting at 10 to the minus 27 times the Planck velocity. It's not even close to that regime of relativity. And we know that they're dark compact objects that are consistent with black holes. And perhaps the best evidence to date that there might be black holes is in certain examples of stellar mass black holes with accretion disks. And now starting with the VLBI, very long baseline interferometer observations of the shadow of Sagittarius A star, there's evidence that there actually are horizons as opposed to surfaces. So again, that's consistent with it being black holes, but we don't have any evidence that says that these actually are the true black holes of general relativity. As I'll say a little bit more later, I think, hopefully in the next few years things are going to change very dramatically with gravitational wave observations and the Event Horizon Telescope, pulsar timing, etc. I just also want to make one comment is talking about the strong field on the scales of cosmology. And if you look at the dynamics of the universe on scales of the Hubble radius, it is fully within this non-linear regime. I think there's a misperception that it's only really at the Big Bang or the Big Crunch, a place where there's singularities, you have to worry about it. But the definition of if you just take matter that's at the present average density of the universe, expand it up to the Hubble radius, if it were asymptotically fat, a black hole would form. And so that's at any time in the evolution of the universe, on scales of the Hubble radius, we are in this non-linear regime of general relativity. Okay, is it, can we actually probe it in the lab? And at least for a while, there was a very exciting possibility that we might be able to do it at the Large Hadron Collider. So this was this idea being mentioned at this conference before of these large extra dimensions. Over a decade ago, several groups sort of noted that if there were more than 4 space-time dimensions, the actual Planck scale might be much, much lower than what we think by assuming that there are 4 dimensions. Or in other words, if we can actually probe sufficiently small scales, then we can see those extra dimensions. We notice that gravity is a lot stronger. And these extra dimension scenarios don't tell you, well, it doesn't have to be stronger, it could even be weaker. It doesn't actually tell you what the true Planck scale is. It just says it doesn't have to be the one that we get from dimensional analysis. And they argued that perhaps a natural choice for a Planck scale would be a TeV to solve the hierarchy problem, to make gravity essentially of comparable strength to the other forces. And soon afterwards, people sort of realized that a generic consequence of this would be that if you collide particles at energies above the Planck scale, you generically form black holes. So unfortunately, as of today, there's no evidence for black hole formation at the LHC. So that's starting to stretch the naturalist arguments a little bit. Who knows how natural that argument is, but in principle, if you can get collisions above the Planck scale, you can form black holes. Okay, so the rest of the talk I'm going to then focus on this, on some questions related to black hole formation and relativistic collisions. But I just want to sort of pose a question which I can't answer right now. So one sort of in a very broad language said that there is this regime, this dynamical strong field. I've said black holes live there, the universe on large scale lives there, these ultra-relativistic collisions live there. I'm not sure that they really are necessarily the same regime, the same limit of the theory. So in some sense, the way that I defined it, right, they're all in the strong field. And in particular now, I'm going to focus on these ultra-relativistic collisions. And there are some very stark differences between the phenomena in this regime and, for example, the astrophysical strong field. First, when we collide objects at ultra-relativistic velocities, and I'll get more into this in a second, it's conjectured that the source is irrelevant. In other words, it doesn't matter if you collide little black holes, little solitons that I'll show you, or even take the infinite boost limit and collide gravitational shock waves, the matter is irrelevant. And so it really becomes a property of just the gravitational, or the geometric side of the theory. Another interesting thing is that in these collisions we can start from, if we look at the finite boost limit, we can start from solitons or particles where the curvature is arbitrarily weak. And for example, just take the LHC, you smash 2 protons together, just take one proton in isolation, go to the rest frame of that proton. What is the curvature produced by that proton is completely insignificant. But if you could accelerate it to ultra-relativistic velocities, in principle, that, or in the rest frame with an arbitrarily small curvature, can still lead to black hole formation. And so the interesting thing in that sense, when we do accelerate these particles to high velocity, in some sense all the energy is kinetic energy, it's not associated with curvature. And if we then look at the collision, it's really the energy associated with the disparity in the reference frames. If we had a single isolated object that we accelerated to high velocities, we could go to its rest frame, the energy would just be its rest energy, so it would be low energy. Going to any large velocity for one particle, that's just a Lorentz transformation, it's just a boost. But now we have two particles that are moving towards each other at very high velocities. Then, in some sense, the minimum energy is the center of mass energy, and then there's a lot of energy just in the kinetic energy. So when we look at this collision problem, we're essentially locking this into the geometry. And there are other interesting things about this ultra-relativistic collision problem, which I'll also try to explain in the end, is if you think, okay, well, I described very heuristically that this regime of relativity is where the most nonlinear dynamics arises, we get black hole formation, or I can do more nonlinear than that. And if you think, well, even amongst all of the situations we can imagine forming a black hole, if we collide them going to ultra-relativistic velocities, that should be the extreme nonlinear regime. Yet a lot of things simplify quite drastically. What I'll try to argue is that what really happens, you can almost understand it just almost entirely in terms of geodesic focusing arguments and Kipthorne conjecture, which I'll get to in a couple of seconds. Okay, so let me now discuss this conjecture. So again, so this is scenarios we have, and I'll say a second just one little bit about quantum mechanics, but this talk is essentially all going to be classical. So we have two classical particles, solitons. We boost them towards each other with high velocities, and we ask what happens. Now, the conjecture is that generically at sufficiently large velocities, they're always going to form black holes. And essentially the reason is because of Kipthorne's loop conjecture. So, well, I say this is a slight sort of liberal use of the original loop conjecture as I understand it, Kip formulated it. So what Kip was looking at a few decades ago, he was looking at a scenario where gravitational collapse was occurring. So a singularity was going to form, and he was wanting to sort of answer the when, or at least come up with a criteria for when does a horizon form to close the singularity, or when is it a naked singularity. So for example, looking at cylindrical, so spherical collapse, we generically form horizons, but long spindles that collapse of cylindrical shapes in 4 dimensions at least, we generically even form naked singularities. And so this conjecture was, well, when you form a horizon, when you form a naked singularity, if you could take a hoop of radius, the Schwarzschild radius of that amount of energy and matter that you're collapsing, and in any way in which you sort of can rotate this hoop around this matter, if it doesn't intersect the matter, in other words, it's morally spherical, then a horizon will form as opposed to naked singularity. So the way that this conjecture has been applied in this collision problem, it's been applied as a criterion for determining whether gravitational collapse will begin in the first place or not. So not that gravitational collapse is happening, it's will gravitational collapse happen, will a black hole form. So here the way that it's specifically done is, so we take our, so this is what I described before as the loop conjecture. So now the way that it's applied to the collision of two particles, so we take two solitons, two particles with rest mass m, so in their rest frame, this is their total mass. They've got some characteristic size, and we boost them towards each other in the center of mass frame with a Lorentz boost factor of gamma. So the total energy is 2m gamma c squared. And so here, the way the loop conjecture applies at the moment of collision, if the effective Schwarzschild radius corresponding to this energy is greater than the characteristic of the size of the particle, then the conjecture is not a black hole. And so this is the only bit about the quantum mechanics I'm going to say. So where the Planck scale comes in, if you want to ask, well, let's suppose these are fundamental particles. what is the characteristic width that you use for them. If you use a de Broglie wavelength, then you get to Planck scale. But in some sense, all of this is classical. Okay, so it's a bold conjecture, and so what would be the evidence to support it? Well, first is that there are two important things about both of them that have to be true. One is that it would have to be completely generic. It cannot depend on how whatever is sourcing this gravitational field interacts. So whether it's black holes, fundamental particles, classical subatoms, it shouldn't matter. And the second thing is that an interaction is key. So somehow, when this collision happens, the gravitational interaction should induce collapse so that the loop conjecture is valid. Because if you just think of, say, taking a single particle and looking at it well before the moment of collision, you can always boost it to a sufficient energy such that the Schwarzschild radius encompasses the individual particle, but it doesn't collapse. It's just a Lorentz transformation. So it's key that there's some gravitational interaction that happens that induces collapse. And it's not clear, at least it wasn't clear to me back when I got interested in this, that this would be generically happen. But I think now over the years, and especially in the last few years, quite strong evidence has been gathered that indeed is the case. So the first bit of evidence was back by Penrose in 1974, when he looked at the infinite boost limit. So that's an interesting limit in the sense that if you take so he looked at these boosted Eichelberg-Sexel solutions. So you take a Schwarzschild black hole, you boost it to infinite gamma factors, but at the same time you let the rest mass go to zero, such that gamma times the rest mass is finite. And then all of the geometry is Lorentz compacted onto these two plane-fronted gravitational shock waves. It's Minkowski on either side. And so what Penrose did is he superposed these solutions, and you can do that with Minkowski on either side. And he found that there was a trapped surface in that construction. So he wasn't able to evolve to the future of that. But if you assume cosmic censorship holds, if there's a trapped surface, there's going to be a black hole. Since then, there have been other studies, and I'm just going to show you a couple of examples from numerical studies how we simulated the finite boost and showed that this, at least in a few examples, that this is indeed what happens. So the first example that I'm going to show you, it's now several years old already, and probably a lot of you have seen this, so I apologize for those that have seen these movies multiple times. This is work with Matt Choptik on the collision of so-called boson stars. So to test this conjecture, at the time I didn't believe that it could work generically. Of course, if you collide two black holes, they're going to have to merge to form a larger black hole. So we wanted to choose matter which its natural inclination would not be to stick together. So it would be as far from the root of this example as you can get without the gravitational interaction. And boson stars are sort of good candidates for that. So a boson star is a solution to the Einstein-Klein-Gordon equations.